In this segment, I'm going to talk about acid-base physiology. Now, I'm looking at an acid-base system here, and I've defined that as two organs, the lung and the kidney, and the blood vessels connecting them. I've put the chemical reaction, CO2 plus water, eventually leads to hydrogen ions and bicarbonate. And I've deliberately put the CO2 under the lung, the hydrogen ions and the bicarbonate under the kidney. So the lung is responsible for controlling CO2. If CO2 rises, the lung can exhale more CO2. If the CO2 falls, we can retain more CO2. On the other hand, the kidneys are controlling hydrogen ions and bicarbonate. First example up here, I'm showing the kidneys recovering bicarbonate and getting rid of hydrogen ions. And now this is probably because of an acidosis. Get rid of hydrogen ions, recover bicarbonate. Well, the kidney can do the opposite as well. In the case of alkalosis, the kidneys can recover hydrogen ions and then dump bicarbonate ions. The next thing you should be familiar with is the Henderson-Hasselbalch Equation, which states that pH equals 6.1 plus the log of the bicarbonate concentration over the CO2 concentration, and I have listed the CO2 concentration here as 0.03 times PCO2. 0.03 is the solubility of CO2, PCO2 is the partial pressure of CO2. Solubility times pressure gives you content or concentration. So the bicarbonate concentration over the CO2 concentration. Now let's try and solve for pH equals 7.4. So if I put 7.4 over here and then subtract 6.1 from both sides of the equation, I get 1.3. 1.3 equals the log of the bicarbonate concentration over the CO2 concentration. For the pH to be 7.4, the log of 20 would equal 1.3. Therefore, we should have 20 times as much bicarbonate as CO2. If the bicarbonate concentration goes up, say it goes up to 48, then I have to increase the CO2 concentration, double it, in order to get back to 7.4. If the numerator changes, the denominator must change in the same direction in order to compensate for the original change. So if there's a disturbance in bicarbonate, a metabolic alkalosis or acidosis, the bicarbonate concentration will change. The CO2 concentration must change in the same direction to get us back to the pH of 7.4. Now this may be complete or it may be partially compensated for. The direction of change of the disturbing variable must be balanced by a change in the compensating variable in the same direction. If the disturbing variable increases, the compensating variable must also increase in order to get back to or at least near the original 7.4. I usually look at lab results and ask three questions. First one is, are we suffering from an acidosis and alkalosis, or is the pH normal? And that's the easiest of the questions. You just look at the pH data. If it's above, say, 7.45 or below 7.35, you can easily determine the acid-base status. I then say, well, what caused the disturbance? If it's an acidosis, the disturbance could be caused by high CO2, or it could be caused by low bicarbonate. An alkalosis, just the opposite. So if we have an acidosis and I determine that the CO2 is high, then I say, well, we must have a respiratory acidosis. If the bicarbonate were low, then we have a metabolic alkalosis. If the CO2 were high and the bicarbonate were both low, both of these is contributing to the acidosis, and we have a mixed acid-base disturbance. So I then ask, was there compensation? If we're using the same example of acidosis, that this is a respiratory acidosis, the CO2 is too high, did the bicarbonate go up? If it did, then we have compensation. If it were a metabolic acidosis, then that means that the bicarbonate concentration was too low. Did the CO2 concentration go down to compensate for the metabolic acidosis? So if you ask yourself those three questions, you should be okay. Two other topics I wanted to bring up were anion gap, and I'm not going to spend any time on anion gap other than to say that it is the difference between the cations, the measured cations, and the measured anions. So sodium is the most commonly measured cation, although you will see potassium, it's in low concentrations. Most people ignore it. So sodium concentration minus the combination of chloride and bicarbonate. The difference between those is called the anion gap. If you remember your laws of chemistry, the sum of all the anions must equal the sum of all the cations. In this case, we do see a difference between cations and anions, owing to missing anions or cations from the lab results. And I will leave that there so you can go back and read up on anion gap. Another concept I want to mention is base excess, and I'll talk about that when I do the models. Base excess is the amount of non-volatile base or acid added to the system. If base excess is positive, there is more non-volatile base in the blood than normal. If the base excess is negative, then there is more acid in the blood than normal. Some people refer to a negative base excess as base deficit, but we'll consider base excess positive as too much base excess negative as too little base. Now I'll move to the computer model so we can examine what's going on with CO2 and bicarbonate and how it affects the acid-base system of the blood. In this model, I can decrease PCO2 by hyperventilating, increase PCO2 by hypoventilating. I can change bicarbonate concentration, increase bicarbonate concentration, or decrease bicarbonate concentration. What I'm looking at over on the right-hand side are the values of PCO2, bicarbonate, and pH. These are the values that are included in the Henderson-Hasselbalch equation. And down here I'm looking at base excess, and I'll describe base excess in just a moment. Along the horizontal axis, we're looking at pH, with 7.4 being the normal average pH, and the dotted lines here representing the normal range. And I'm a little bit conservative here. I'm using 7.36 to 7.44. Many people use 7.35 to 7.45. Along the vertical axis, I'm looking at bicarbonate concentration in milliequivalents per liter, and the normal value is approximately 24 milliequivalents per liter. Since CO2 is involved here, we need a third dimension. We display that third dimension with these isobars, or isopleths. This is 150, 110, 80, 60, 40, which is the normal, and then down here, 20, 15, down to 10. Normal PCO2 is about 40, a range in here somewhere between 36 and 44. Some people use 35 and 45 as the normal range. And this line right here is called the normal buffer line. The normal buffer line describes the amount of buffer in the system, protein buffers. The amount of protein buffers in the system will determine this normal buffer line. Normal protein buffers include albumin, include hemoglobin, for example. If there were no protein buffers in the system, the buffer line would have a slope of 0. It would be perfectly horizontal. We need proteins in the system to remove hydrogen ions to allow the reaction CO2 producing hydrogen ions of bicarbonate to cause the bicarbonate to go up. More protein, the steeper this line would become. Hypoproteinemia would create a less steep buffer line. This is the normal buffer line we see in the average individual. If I increase CO2 simply by hypoventilating, bicarbonate is going to go up. But bicarbonate is going up not because of any change in titratable acid, simply because carbonic acid has increased because of CO2. Base excess then becomes very important, because if I do come up here and say we're now at PCO2 of about 80, we have an acidosis. It's a respiratory acidosis, and you ask the question, was there compensation? Well, the bicarbonate concentration went up, but the bicarbonate concentration went up solely because CO2 went up. It had nothing to do with the kidneys trying to adjust the bicarbonate concentration or adjust the pH. Base excess is 0. No titratable acid has been added or removed. No titratable base has been added or removed. Now I've increased the bicarbonate concentration. Now we see the base excess is 5.7. So clearly there has been some base added to this system to try to compensate for the low pH. pH has gone up a bit. So the base excess of 5.7 then is determined by taking the measured point and going straight down to the buffer line. So here I have 32. I come down to the buffer line, which is just a little over 26 here. So the base excess is 5.7. Anywhere along this line I put this, base excess is still 5.7. I'm still 5.7 units above the normal buffer line. Why do I point that out? The normal range of base excess is plus or minus 2. So the base excess then, from here to here, would be plus 2. The base excess from here down to here would be minus 2. So plus and minus 2 represents our normal range. So if I were to do this, we would have to say the base excess is within plus or minus 2. Therefore, we cannot assume any renal compensation for this respiratory acidosis. So let's hypoventilate this individual. I will bring the CO2 up to 60. We now have a pH of 7.25. Clearly this is a respiratory acidosis. The only thing that changed was the CO2. There's been no compensation. Base excess is 0. Bicarbonate has risen, but it has risen only because CO2 has risen. Kidneys have done nothing yet. So this is a clearly uncompensated respiratory acidosis. If the kidneys now try to recover the pH by excreting hydrogen ions and recovering bicarbonate, let's bring this up to here. Bicarbonate has come up to 30. Base excess is nearly 5. Clearly there's now an increase in base added to the system. So this is a respiratory acidosis. Again, we ask the question, pH is 7.3, we have an acidosis. It could occur because of high CO2 or low bicarbonate. In fact, now we have high CO2. And the third question is, did the bicarbonate concentration go in the same direction as the CO2? Since CO2 went up, we asked, did the bicarbonate also go up? It did. We can see that from the base excess. Positive base excess, increase in bicarbonate, now to 30. This individual has been compensating for the respiratory acidosis. The kidneys have been compensating for this respiratory acidosis. Not completely, because we're not back in the normal range yet. But nonetheless, we've improved the acid-base status from where it was. Let's try a few more of these. Let's move the values here and here. And let's ask ourselves this question again. Is this an acidosis or an alkalosis? 7.53, clearly an alkalosis. Alkalosis caused by either low CO2 or high bicarbonate. The CO2 is low, therefore this is a respiratory alkalosis. Now, the next question, did the bicarbonate go in the same direction? So the PCO2 went down, the bicarbonate should go down in order for there to have been compensation. Clearly it has gone down. We have a negative base excess. It's down to about 16. So this is a partially compensated respiratory alkalosis. So let's try another one. Here we have pH of 7.3, acidosis. Second question, either low bicarbonate or high CO2. 14.9 with a negative of almost 10 base excess clearly tells us this is a metabolic acidosis. If the bicarbonate went down, then the CO2 should also go down in order for there to have been compensation. The CO2 went from 40 down to 31. Clearly the CO2 did go down to compensate for the low bicarbonate. This, therefore, is a partially compensated metabolic acidosis. Now, what's happening here? We have an alkalosis, 7.67. What caused it? The two things that could cause it would be low PCO2 or high bicarbonate. Well, the PCO2 is low and the bicarbonate is high. Clearly, this is a mixed acid-base disturbance, combined effects of respiratory alkalosis and metabolic alkalosis. Well, that concludes the discussion on acid-base physiology.